My name is Binju, and I'm a research fellow in the University of Surrey. And today, continuing to my box presentation, I'm going to introduce more details about the residual stress evaluation using larger facilities, including neutron diffraction and neutron Bragg imaging. So this is the outlook of today's presentation. We start with the background a little bit and introduce the residual strain or stress characterization from 1D to 3D, and then show how we correlate the residual stress distribution with the mechanical performance. First is the background. So this project is based on the nuclear fusion reactor. We have many fusion reactions, but the DT fusion reaction is selected for the to commercialize this nuclear fusion energy industry, and it is green energy because we can find the DT source from the natural, and 60 kilogram of fusion fuel can generate lots of energy, which is equivalent to 250,000 tons of petrol. So scientists have already proved the feasibility of this whole processing, but there's still a lot of challenges, including both physical parts and engineering parts. So for physical parts, it's more like how to control the plasma during the operation. And for the engineering part, which is our focusing, is to enhance the safety and the maintenance strategies for the nuclear fusion reactor and make sure it can last as long as possible. So in Europe, there's a lot like ongoing projects like ITER, DEMO, and STEP. And in all of that projects, the Euro 97 is one of the construction materials to build up the reactor, and it can be joined with other materials or itself to achieve different function. So in that case, the joint of the Euro 97 steel is quite important to make. We need to make sure the lifetime for such joint to make sure the safe operation of the reactor. And there is one of the techniques which will be frequently used during the operation, which is remote laser welding. And during the welding process, although it can seal the cracks or fix the problem, but it also induced a lot of like residual stress in the components. So a little bit more about the residual stress. So it is built-in stress after all the external loads removed. And in the materials, it can the detrimental residual stress can aggravate the crack initiation or the crack propagation. And also, if it's a beneficial residual stress, it can resist the crack and make the components last longer. And it has 3 types of scale, including from type 1 to type 3, from the macro to the micro. And different kinds of scale of residual stress can have different interaction with the mechanical properties. So in our case, we need to learn that in multi-scale. And here we are going to use the neutron diffraction to start that, like most likely the type 1 residual stress. And the results can contribute to the modeling establishment and can also contribute to the design protocols or protocols for the nuclear fusion reactor. So here are some a quick view about how to measure the residual stress in general, and they all have pros and cons. And in this project, we use the neutron diffraction and the neutron imaging because the neutron can get into the materials, and we can know how the residual stress distribution within the materials. And for the imaging, because the detector has relative high resolution, so we can look at more detailed distribution, especially in some like narrow heat-to-factory zone. Here is the results for firstly the one-dimensional residual stress measured by the neutron diffraction. So we've done that experiment twice. One is at the NJX, and we do the scanning at those points. And we have the residual stress distribution in both in-plane directions and also zero thickness directions. And we have the results presented there. And we also done the same characterization at the same place at the SELSA, but the resolution for the SELSA is like almost 2 times higher than the NJX, and we correlate the results from the 2 beam lines, and we can see they are in a good consistency with each other, even the resolution is different. And we can also find a edge-shape distribution here, and from the results we can find there is not too much variations in the zero thickness directions. So even the resolution of the SELSA beam line is relatively higher, but it's still not high enough to characterize the narrow heat-to-zone region in this litho welding sample. So in that case, we use the neutron imaging to look at more detailed residual stress distribution, because the spatial resolution can be up to 200 micron. And we also apply the imaging techniques to apply the position dependence, the D0 value to this map, so it can accurately characterize the residual stress distribution. And we also correlate the Bragg imaging results with the neutron diffraction, and it showed that bottom right corner, we can see the results is quite good consistency between the 2 techniques. But this technique also has some drawbacks, especially for the materials with high textures. We can see the analyzing procedures, if the materials has higher textures, the edge broadening and edge shape can affect the analyzing results. But unfortunately, but luckily, in these materials, it's only compromised a little bit. It's not because the materials is not high textured. And another drawback for this technique is only provides the high resolution at the in-plane directions. So if we want to know the residual stress distribution at the zero thickness directions, we then need to apply the 3D tomography techniques to reconstruct the strains in both in-plane and zero thickness directions. So we've done this reconstruction with very limited number of projections. So the resolution is not perfect. It can only it's been compromised to 2 millimeter. But we can still find the trend of the residual stress, and we can also reconstruct the structure of the welding pool. We continue to do this research, and we've done the experiments 3 months ago, and we will continue to do this research to fix how to reduce the scanning time and acquire the projections in a cost-effective way. And we also try to find a method to overcome another assumptions, which is the isotropic strain field. So at the last, after the characterization, we need to know how the residual stress affects the mechanical properties. So we've done 2 in-situ tests, one with the DIC work and another with the neutron diffraction, to see how the residual stress affects the mechanical properties. And we can see from here, the full field DIC show the welding pool has less strain compared to the rest of the area at the same stress state. And look at the detail at different stress states, we can find the variations in that curve And that's kind of the residual stress effects. And at the higher stress fields, which is over yield stress, or which is over where has the large deformation, we can find the residual stress effect is not that distinct, and it's most likely the microstructures dominates the deformation mechanism. And the same phenomenon can be also found in the neutron diffraction characterization. And at the beginning, we can clearly find the residual stress distribution, but after yielding, we can find the materials, the residual stress effect is not that clear. It's already merged into the large deformation caused by the microstructure effect. Here is the detail of the 3 publication, including all the results here. So if you are interested, you can have a look at the detail. And thank you for your attention.